This is a lecture from OpenTuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
All right, this is the second lecture on the chapter on semi-variable costs. So I've already explained what we mean by semi-variable, and I showed you one approach, the high-low method, which is a nice, simple, quick approach, but I explained in the last lecture why there was a problem, why it perhaps was slightly dangerous. Well, regression analysis, again, as I said at the end of the last lecture, will take account of all the observations and give a much better estimate of the fixed and variable, but it is rather more complicated. I did explain when we went through the last chapter that any cost, that we can have an equation that the total cost is always equal to the fixed cost. Oh dear, what's going on? Start again. The total cost will be equal to the fixed costs plus the number of units times the variable cost per unit. Now, although you can use all sorts of symbols, I could write that as saying if the total cost is y, it's going to be equal to the fixed cost. Well, the fixed cost could be anything, could be 1,000, 10,000, whatever. Let's say A plus the number of units x times the variable cost per unit b. Now the point is that's a sort of equation we'd end up with. You know, it may be 10,000 plus b, $2 times the number of units. It may be 50,000 plus 3 times the number of units, and so on. But our job is to find out what is the fixed cost, what is the variable cost per unit. And this regression, I'll show you basically where it came from, but it's not your job to prove anything. There are formulae that are given you in the exam to calculate the value of A, the fixed cost, and the value of B, the variable cost per unit. They're given you in the exam, and I've typed them here, and you can see B is N, sigma X, Y minus sigma, and they're both quite messy. Now, we're going to work through an example. I explain what the symbols mean and how we do it. In the exam, you're not going to have to do a great full one, but any one bit of this could be asked you, so you've got to be capable of doing a full one and understanding. And let me use example 2 to explain how we use the formula, what the symbols are. And firstly, well, we'll set it up as a table. If you look at example 2, it says the following table shows the number of units produced each month and the total cost incurred. So just like the previous one, but with different figures. In January, we produced 100 units and the cost was 40,000. In February, 400 units, the cost was 65,000. March, 240, and so on. Got a whole list. Well, let's list those as a table. And for purposes of using the formula, we're going to need what's x and what's y. Well, think about it. X is the independent variable because the total cost y is going to depend on the number of units. So I'm going to set up a table. X will be the number of units. Y will be the total cost. And let's list them all. January, there are 100 units. the total cost was 40,000. Now, before I go any further, two things. There's a lot of multiplying involved here and numbers and things. And although the actual cost is 40,000, and by all means do what we're going to do on the actual cost, it is going to mean huge numbers in the calculator. And writing lots and lots of zeros, we end up all over the place. And so what I'm going to do is I'm going to write the cost in thousands. So instead of writing 40,000, I will write 40, as was in the actual question. But also the number of units. If you look, they're all in hundreds. So although by all means use 100, 400, 200, just to keep the arithmetic a bit shorter, I'm going to write it down in hundreds. So instead of writing 100, I'll write 1. And for February, instead of writing 400, I'll write 4. And the cost 65. Now I'll have to remember at the end what I've done, but it's up to you. If you're happy with your calculator, write them in full. 100 units, 40,000, 400 units, 65,000, and so on. But you'll see, because of what's coming, the smaller we can keep the numbers, the easier, the quicker it'll be. But let's carry on. March, 245,000. April 780,000, May 670,000, 570,000, 350,000. All right, now look back at that formula. There's a formula for B, a formula for A, and if you notice, the formula for A has B in it. So we have to do B first. And the formula for B, you've got it in front of you, but if I write it down, it's N, this symbol is called sigma xy, minus sigma x, sigma y, divided by N, sigma x squared, minus sigma x, all squared. Now what the symbols means, and this, remember, although you're given a formula, you're not told what the symbols mean. N is the number of sets of observations. Now what I mean there is, for this question, we looked each month. We had January 100, cost 40, February 400, cost 65, and so on. How many sets of observations were there? Well, one set for each month, January, February, March, April, May, June, July, is what? 7 months. That's an easy one. The number of sets of observations. We know what X and Y are. X is the number of units, Y is the cost. Well, the symbol sigma means sum of, or total of, whatever comes after it. So although we've got lots of them here, sigma x, for example, simply means it's the total of what comes after it, all the x's. Sigma y is the total of all the y's. So before I go any further, let's calculate those. Sigma x is the total of all the x's. Well, 1, 5, 7, 14, 20. I think it's 28. The total of the sum of all the x's. Sigma y is the total of all the y's. So 40 plus 65 plus 45 plus 80, 70, 70, 50. 420. No problem. So sigma, we just add them up. What else do I need for the formula? Sigma xy. Well, sigma means the total of, but whatever comes after. Xy So we need to multiply x by y each time and then add them up. So let's multiply x times y for each of them. 1 times 40 is 40. 4 times 65 is 260. 2 times 45 is 90. 7 times 80 is 560. 420. 350. 150. In each case, I've multiplied x times y, and then I add them up. So the total, 40, 260, 90, 560, 420, 350, 150. The total is 1870. That's the total of all the x times the y's, or sigma xy. What else do we need for the formula? Well, we've got sigma x, sigma y, sigma xy. Now there's sigma x again. We need sigma x squared. So let's get x squared each time and then add them up. X squared, 1 squared is 1, 4 squared is 16, 2 squared is 4, 49, 36, 25, 9. In each case, I've squared x, add them up, and we get 140, the total or sigma x squared. So I've now got everything I need for the formula. We've got sigma x, sigma y, sigma x squared, sigma xy, and n is 7. So now let's stick them in the formula. I'm going to erase this, and I've got room because I need to be able to see the figures. I don't want to keep going up and down. So b, n is 7, times sigma xy, I can't see them. There we are, 1870, minus sigma x 28 times sigma y 420, divided by 7 times sigma x squared is 140, minus sigma x all squared, 28 squared. Now, I don't know, if you're really efficient with your calculator, you can use brackets, you can perhaps do all that at once. Just for everybody's benefit, let me do it step by step. So the top, 7 times 1870 is 13090. 28 times 420, 11760, divided by 7 times 140, 980, minus 28 squared, 784. So we're almost there. What does that come to? The top bit, 13090 minus 11760, 1330, divided by 980 minus 784, 196, which finally gives us b equals 6.7857. Now we've got a figure for b, we can work out a. Because if you look back at the formulae, which yet again you will be given, a is sigma y over n minus b sigma x over n. And so this is pretty quick. Sigma y from our table was 420, and if you remember was 7, minus b 6.7857 times sigma x, which was 28, over 7. 420 over 7 is 60 minus, what does that come to? That 27.1428. So B equals 32.8572. So we now know the values for A and B, and appreciate it is really a question of speed on your calculator. Remembering what the symbols mean in the formulae. Although, as I have said, you couldn't be asked to do a whole one in the exam, but any bit of that can be tested, proving you know what sigmas are. If I gave you the totals, proving you can calculate A and B, and so on. Just one thing to be careful of here, which probably won't be a problem in the exam. But I said that A and B are the figures for the formula. So y equals A, 32.8572, plus B times X. B was 6.7857. Y, remember, is the total cost. X is the number of units. So the total cost is the fixed cost plus the variable cost. The only thing we need to be careful of here is, remember, the X and Y I used, my X's were in hundreds. So, you know, if you wanted to use this formula to say, what's it going to cost if we make 1,200 units? You'd have to put X equals 12. And also, Y was actually the cost in thousands. And so, if I got an answer of 58, it would actually mean it was 58,000. And so to correct for that, in fact, Y, well, remember, it's not actually going to be 32 plus something, it's 32,000 plus something. So it's 32,857, I'm not worried about 0.2. Plus, well, again, we need to multiply by 1,000, 6,700 and something, but that was for every 100 units. So I multiply by 1,000 divided by 100, it's plus 67.857, I'll put 0.9x. Now think about that, although to get over worried for that last bit is unlikely for the exam. Usually the numbers they give you in the exam would be easy, small numbers anyway. I appreciate here, I said I could have done it from the very beginning and put 140,000. Then I wouldn't have needed that messing at the end. But it would have just meant all these figures would be so big that we get the danger of getting lost on your calculator, with so many zeros. Anyway, there we are. 32,857 will be the fixed cost. 67.9 would be the variable cost per unit. So again, we've split the semi-variable cost into fixed and variable. And for the reasons I explained earlier, it's a somewhat better approach than using the high-low, because it takes into account all the observations. I've then left a huge amount of space for not very much. What are the problems with this? Why is this not perfect? Well, there are two reasons. One is, I mentioned before, if you did put them all on a graph, then in fact, it's not exactly linear. In fact, this one certainly isn't. Look back at the question of May and June. May and June, they both have the same production. Sorry, I beg your pardon. They have different levels of production, but the same cost. It's not exactly linear. And so any answer we get is only really approximate. But at least, we've found the line that most nearly goes through them. I think I said enough about that. The other problem, though, is we have assumed that it is basically linear. It could have been that if we'd put them on a graph, maybe it looked like this. Now that's clearly some sort of curve. It's not a straight line at all. It's nothing like a straight line. And yet we can still use the formula and we'd come out with some sort of line that goes through it. But we have assumed right from the beginning that it was basically a linear relationship. Well, it might be an idea to check. All right, we could draw a graph and see, does it look like a line, or is it more of a curve, or is it just all over the place, Well, we're not going to draw a graph, but there is a way you can check to see how linear it is. And it's the next section. It's something called the correlation coefficient. Now, it won't take us long, but yet again, to avoid these lectures getting too long, I'll pause and we'll work through this in the next lecture. So if you're at all unsure, make sure you go back and you're happy with what we've done. And if you are doing this with me, don't throw away that table, because you'll see we are going to need that in the next lecture. So, I'll stop this one here, but just one more lecture for this chapter and then we've got it.